Okay, so here we go. So what do we got? Number 5 on worksheet, what is this, 6.3? Okay, so here's what you were told. You were told that Roy, I assume, is trying to move a piano up 2 meters, right? He's trying to lift it up into a thing. And so he's going to do that by using a ramp, because pianos are heavy. And so in part A, he uses a ramp that's, I think, 3 meters long, right? So here's your ramp. We know that we're lifting it up 2 meters. We know that, oops, I guess I could put units on that. We know that this guy here is 3 meters long. Here's your piano. The problem tells you it has a mass of 500 kilograms. All right? And so the question wants us to make a free body diagram and then calculate the work that Roy is going to do moving this thing up the ramp. Okay? So, to make my free body diagram, I guess the first thing we need to do is, so every time you make a free body diagram, you start with gravity, right? But because this is on an inclined plane, I'm going to have to somehow take that force of gravity and split it up into components, right? Everybody okay with that logic? Okay, so let's see. Our force of gravity is going to be 500 times 9.8, so you get negative 4,900 newtons. I'm going to put a smiley face. All right. Now, in order to find my perpendicular and parallel components, I'm going to have to do a little bit of trig. And I think the worksheet even said, hint, you need to find this angle first, right? Okay. So, let's see. We know the opposite and the hypotenuse, so I think we can use inverse sine to find that angle. And you get like 41.82 degrees or something like that. 41.8 something. I'm going to say 2. All right, everybody get up to there. Okay, so now what I can do is I can take this force of gravity and split it up into components. All right, so your FG parallel ends up being negative 3,000, is it 266?
Yes.
Thank you. I guess I could have, I don't know, I'm getting mad at you. I'm the dummy that doesn't have my answers in front of me. All right, so there's your FG parallel. Okay. And there's also an FG perpendicular, which actually doesn't really affect this problem, right? So why does the FG perpendicular not matter?
Because the normal force just cancel it out.
Okay, actually for 2 reasons. Good. There's a perpendicular component. Give me 2 seconds, Abby. There's an FG perpendicular. You okay?
Oh, yeah. Yeah,
Okay. Okay.
Yeah.
So that perpendicular component is going to get canceled out by the normal force. Secondly, there's another reason. This problem is about work. You got an idea?
Well, is it because it's perpendicular to the motion?
Very, very good. Yeah, look, you guys, everybody point for me. Which way is the displacement of the box? Up the ramp, right? So draw a little arrow and label it displacement. Okay? So remember, you guys, when we use this equation over here, force times displacement times cosine of theta, that theta represents the angle between the displacement and the force, right? And by definition, my perpendicular component is perpendicular to the ramp, so it's perpendicular to the motion, right? Okay, so I really don't care about either of these two forces. A, because they cancel, B, because they don't do any work. Cool? So I'm just going to do this. I'm just going to draw another smiley face, because like I said, smiley faces are nice. All right. But I can put my FG parallel on here. FG parallel is negative 3266.6 repeating. Problems. Did I do any of that too quickly for anybody? Okay, cool. So, the question wants to know how much work Roy is going to have to do. So in order to find the work done by Roy, I need to find the force exerted by Roy. So if Roy's goal is to slide this thing up the ramp, assuming it starts and ends at rest, how much force does he need? Yeah, 3266 again, right? Okay, it's just like this problem. Remember yesterday we were talking about lifting the 35 kilogram thing? And we said that the force that you exert while you lift it averages out 343? Same idea here. To get it moving, we're going to need a little more force than this. To stop it, we're going to need a little less, but everything kind of averages out. And so our force of Roy, technically it's an average. Somebody first hour got really mad at me for not writing that, but there we go. Cool? Any problems? Okay, so that's my free body diagram. Now it wants us to find the work. So the work done by Roy is equal to force of Roy times displacement times the cosine of the angle, right? So let's see, the force of Roy, we just found it. That's 3266.6 repeating newtons, right? Because that's what we just found. What's the displacement, 2 or 3 meters? 3 meters, right? Because the block, or the piano rather, is moving from the bottom of the ramp to the top of the ramp. 3 meters, right? Times the cosine of 41 degrees, right? Because that's how steep the ramp is, correct? No. No. It's not 41 degrees. Super, super common mistake. All right? What does, in this equation over here, in my cluttered board over here, what does this theta represent? It's not the angle of the ramp. It's the angle between,
The displacement of the force.
it's the angle between the force vector and the displacement vector. So everybody point for me. Which direction is Roy pushing? That way. Which direction is the box moving? That way. What is the angle between those two vectors? 0. Okay. Remember yesterday I told you anytime your force and your displacement are parallel, you don't need to worry about this because cosine of 0 is just going to be 1, right? That's a 1. Follow? So multiply this out and you get 9,800 joules. Does that make sense, you guys? We good? Cool, Sid, you okay over there? Okay, now here's a question that the problem didn't ask. So in my first hour, somebody was like, well then, I don't get it. Give me an example of a time when you would have to worry about this angle. Okay, so let's do this. The problem didn't specifically ask you to, but let's calculate the work done by gravity. All right, so what we did here is we calculated the work done by Roy. Right? So everything here, this is the work of Roy. Okay, let's go over here and calculate the work done by gravity. All right? And there are a couple of ways of doing this. All right? And I think they're both instructive. Okay? Option number 1, just use the equation. The work done by gravity is the force of gravity times the displacement of the box times the cosine of the angle between my force vector and my displacement vector. Okay, so my force of gravity is this, right? 4,900 newtons pulling down, right? Good. Times my displacement, which is 3 meters, times the cosine of some angle. Oop, I don't want to, I'll fill it in a minute. So we got to figure out what angle it is, and it's not at all obvious. Question?
Do you make the gravity negative or do you keep it positive?
So when you use this equation, the cosine of the angle is going to take care of the negative for us.
Okay.
So yeah, anytime you use this equation as it's written, you don't put any negatives in. Okay? But when I get to the end of this problem, I'm going to point something out. It's just a check you need to do, I guess. Okay? So really good question. All right, so now we got to figure out what the angle is. So I'm going to make a new drawing. So check it out. Here's my ramp, right? Or better yet, there's my displacement, right? And which way does gravity pull, you guys? Point for me. Which way does gravity pull?
Down.
Down, right? So those are my two vectors. I want to find the angle between them. So I'm looking for this angle here, theta. I don't know why I drew that as a dotted line. That's the angle I'm looking for. Okay? Now, what's this angle? 41.8 degrees, right? What's this angle? 90 degrees. So what's this angle?
131.82.
Yeah, isn't it just 90 plus 41? Does that make sense? Cool. Any problems with that? Okay, so this is the cosine of 131.82 degrees. Anybody got a calculator handy? Figure that out for me real quick. It gives us a neat answer. 4,900 times 3 times the cosine of 131.82. Yeah, what'd you get?
Sorry, was this supposed to be the top or bottom?
What do you mean? This.
Okay, yeah, so I got a negative, yeah.
It should be negative.
Yeah. Negative 9,801.
Okay, and the and 1 is because this 0.2 is rounded. Some of you are nodding a little bit. What do I want you to notice here?
They're the same.
It's the same, right? Okay, now that won't always happen, and we'll delve into why that happened a little bit more when we get to 6.5 next semester. But that is important, that those numbers are the same. Okay? Basically what it's showing you is that gravity's working against Roy, right? He's trying to push it up the ramp, and gravity's like, and working against him, right? Okay, and we'll later learn that that has a connection with gravitational potential energy and some other stuff. So, anyway, questions on all of that? All right. There is another way we could have found the work done by gravity. Okay, so check it out. Here's another way we could have done the work done by gravity. Bear with me. I don't know if you have to write this out, but at least follow this train of thought. Another way we could have found the work done by gravity is this. We could have found the work done by gravity perpendicular to the ramp and added that to the work done by gravity parallel to the ramp. In other words, gravity has two components, right? There's a perpendicular component and a parallel component, right? Does that make sense? Question or answer?
The perpendicular component, since it's perpendicular to the direction of the force, just be 0?
Yes, that is exactly right. So, if you missed it, what Abby just said is this. She said, damn it, I did it again. I did that yesterday too, didn't I?
Yeah.
Sorry, I don't know why I keep doing that. So, look you guys, the work done by this part of the force of gravity is 0, right? Because it's perpendicular to the motion, right? So this is 0 plus, now, here's the cool part, you guys. Look at the force of gravity parallel. Everybody point for me. Which way does FG parallel point? Down the ramp, right? Which way is the box moving? Up the ramp. So my work should just be negative force times displacement, right? So negative 3266.6 times 3 meters. Holy beans, that's the same thing I did over here. That's a J. Yeah?
You said in the later chapters this won't always work out.
It won't always be true. I mean, everything I just did here is good. Yeah. It won't always be true that the work done by Roy is the same as the work of gravity. Okay? Yeah. The reason it worked here is because the box starts and ends at rest. There's no change in velocity from start to end.
Yeah.
So. Okay. Cool, you guys? Problems? Bless you? Okay. Are there any other ones on the worksheet you guys would like me to go over? Okay. If you're lying right now, in a couple minutes I'm going to say go, and then you should ask me questions if you have them. Cool. All right. Now, about conservation.